Hey everyone, welcome back, and today let's solve Leetcode problem 2493 titled Divide Nodes into the Maximum Number of Groups. So we're given a positive integer n representing the number of nodes in an undirected graph, and there are nodes, or rather the nodes are labeled from 1 to n, right? Meaning we have n nodes. So we're also given a 2D integer array edges, where edges that I simply represents an edge that is bidirectional between the nodes A and B sub I, right? And notice that the given graph may actually be disconnected, right? That means that we don't necessarily need to have n minus 1 edges. It doesn't need to be like a fully connected tree. It can be a disconnected graph. Now we need to divide the nodes of the graph into m groups that are 1 indexed, such that each node in the graph belongs to exactly one group, and for every pair of nodes in the graph that are connected by an edge, a sub I, b sub I, in the edge's input belongs to the group with index x, and b sub I belongs to the group with index y. And if that's the case, we want the distance between those two indices, y minus x, their absolute value or absolute difference, to be equal to exactly 1. Now we need to simply return the maximum number of groups, basically maximizing m, right, the number of groups, into how we can actually divide the nodes, right? And we need to return -1 if it is impossible to group the nodes with these given conditions, right? M groups, and we have to follow that each node in the given graph belongs to exactly one group, and for every pair of the nodes that are connected by an edge, they belong to the group with index x, and b sub I belongs to the group with index y for a and b respectively, and the distance between those two group values, y minus x, should have an absolute difference of 1. So in the examples, to better visualize this, we see n to be 6, and in this case we actually do have 6 edges as well between our nodes. We have 1, 2, 1, 4, 1, 5, 2, 6, 2, 3, and 4, 6 as are the pairs of nodes that share an edge in the graph, and in this case our output is actually going to be 4. Why is it 4? Because that is actually the maximum number of groups that we can actually divide the nodes, such that each node is actually only in one group, and we're also given that for every pair of nodes that are actually connected by the edges, this is where the edges input actually comes into play, the difference in their groups or indices, x and y for a and b respectively, have an absolute difference that are equal to 1. So let's go ahead and see why that actually works and why 4 is actually the correct, accurate output for this example. So we see that we have 6 edges. We also do have 6 nodes because n is equal to 6, and we have an output of 4. And as you can see, we do also have 4 groups that we split our nodes into. That is actually the maximum in our visual representation as well. And now why is that? Well, first of all, to kind of explain this, okay, we have node 5 in the first group, we have node 1 in the second group, we have nodes 2 and 4 in the third, and nodes 3 and 6 in the fourth group. We see that every edge is actually satisfied, meaning that each node actually belongs to exactly one group, and for every single pair of nodes in the graph that actually do have an edge, meaning these pairs 1, 2, 1, 4, 1, 5, 2, 6, 2, 3, and 4, 6, we know that if they're actually connected, they belong to the group that only have a difference, or rather absolute difference, of 1. Right? Now let's go ahead and actually see that in action here. 1, 2 is connected by an edge, and so the group number differences between those two nodes has to be 1. 1 is in group 2, 2 is in group 3, 3 minus 2 is indeed 1. Now let's go ahead and look at 1, 4. 1, 4 are connected, 1 is in group 2, 4 is in group 3, 3 minus 2, the group numbers that they're in is exactly 1. Now even if we took the absolute value of 2 minus 3, that would still be the absolute value of -1, which is still 1. We see that node 1 and node 5 are connected, and we see that node 1 is in group 2 and node 5 is in group 1. 2 minus 1, or the absolute value of 1 minus 2, still gives us 1. 2 and 6, or rather nodes 2 and 6 are connected. Those nodes 2 and 6 are in group 3 and group 4 respectively. Group 4 minus that group 3, 4 minus 3 is equal to 1. Perfect, it meets our criteria. 2 and 3 are also connected that share an edge. 2 is in group 3, 3 is in group 4, 4 minus 3 is 1. And finally 4 and 6 are also sharing an edge. 4 is in group 4 is in group 3 and 6 is in group 4. 4 minus 3, the group numbers that they're in, are still going to be exactly 1. So that's why this meets the criteria. 4 is actually the maximum number of groups that we can form. right? It isn't impossible to form any groups, meaning these constraints, so we definitely do have an option, and in this case, our output would then be 4. That's the most optimal or maximum number of groups that we're trying to optimize here as our output. In example 2, we see n to be 3 and edges to be 1, 2, 2, 3, and 3, 1. In this case, we have 3 nodes and 3 edges, and we see that 1 shares a edge with nodes 1, or rather with nodes 2 and 3, and node 2 shares an edge with node 1, and we see node 3 shares an edge with nodes 2 and 1. In this case, our output is -1. It is impossible to even form any groups, because let's just think about it. We see that 1 is connected to both 2 and 3. So assume we have a group 1 and we add node 1 to that first group. Okay, fine. According to our logic or criteria, we can still add node 2 to the group 2 or the second group, and then we can add node 3 to the third group. That would satisfy the first 2 edges, sure, but then that wouldn't satisfy the third edge, right, with 1 and 3, because 1 would be in the first group and 3 would be in the second group. That wouldn't work because we know that the group number differences between the two have to be at equal to 1. It simply isn't possible to do that because not only do 1 and 3 have to be a difference of group 1 away, but nodes 1 and 2 also have to be a difference of 2 away along with nodes 2 and 3. We have to have 3 groups, and we can actually form it using these criteria problems. So for the constraints here, we see that n, or the number of nodes we have, is going to be within 500, a relatively pretty small input for Leetcode problems in general. We see that the length of our input array edges is basically going to be within 10 to the 4th power and at least 1, meaning this is the number or range of the number of edges we'll have. Edges at index I is always obviously going to have a length of 2 because we only have 2 nodes sharing an edge at one point of time in the input. We're also given that a sub I and b sub I are within n, of course, the number of nodes, and we're given that a sub I is not equal to b sub I because, of course, an edge, or rather a node, cannot share an edge with itself. And finally, we're also given that, or guaranteed that there is at most one edge between any pair of vertices, kind of going along with this constraint as well. So with the problem statement, constraints, and examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would outputtably solve this problem in a few seconds. Okay, so what is one very important observation that we can really make in this problem to help us lead to our most efficient solution? Well, in this case, that really is that this problem is, I wouldn't say straightforward, but really can be approached by basically analyzing each connected component of the graph separately, right? And kind of elaborate what that really means. Effectively, for each connected component, basically we can actually determine the maximum number of groups by actually performing something known as the breadth first search, or the BFS algorithm, to actually measure the depth of that specific connected component. Right? And that depth is basically going to help us understand how many groups that we can actually form while still satisfying the given constraints of this problem, where every single connected pair of edges actually do have a group number of 1, and we do place exactly each node in the graph to only one group per node. Right? And effectively, the way we're going to actually structure our algorithm, basically for the actual graph representation part of our solution, we're basically going to represent the graph using an adjacency list using our input array edges, and we're also going to have BFS traversal, or BFS algorithm logic. Basically, for each unvisited node, we're actually going to perform a BFS helper function to actually explore all of its connected component. And of course, for the depth calculation of that connected component, doing our BFS algorithm, we're actually going to calculate the depth of it. And basically, that depth is going to correspond to the maximum number of groups for that specific component. And we actually need to validate this, right? And the way we can do that is, while we actually traverse the graph, we have to also make sure that the graph is bipartite. Right? I don't know if it's bipartite or bipartile. Either one of those two. I'm going to assume it's bipartite. And we're going to go with that. Basically, what this really means, though, on a high level, basically that means it can be colored with 2 colors, such that no 2 adjacent nodes actually have the same color, right? And basically, if that's not the case, if the graph isn't bipartite while actually traversing it, we know we can return -1 because it would be impossible to group the nodes as required for every single connected pair to have a group number differing by exactly 1. Right? And of course, to actually return a result, we basically have to sum the depths of all the connected components and get the maximum number of groups. So with the solution rundown out of the way, let's go ahead and dive straight into the code here. So what I'm actually first going to do, like I usually do for graph problems, is, you guessed it, initialize the graph. Like I said before, it's basically going to be in the form of an adjacency list of the nodes from our input array edges. And so the way I'm actually going to initialize that, basically it's going to be an empty array, and this is going to be in the range, so for blank in the range as my underscore for my iterator, of n, right? N is again the number of nodes in our graph, and graph at index I is going to store a list of nodes that are all connected to node I in our input graph, right? This is simply an adjacency list representation of the graph input, right? In this case, we're given as an edges, or rather a list of edges. So now let's actually kind of build the graph with every single node's corresponding connected component, or neighbors. The way I can do that is basically for every single u and node v, node u and node v as our iterators, kind of unpacking Python in the edges array, right? Basically, to actually build the graph, we'll set graph at these two node indices. So first we'll do graph at u minus 1, sorry. And the way I'm going to initialize this is basically append it, v minus 1. And very similar logic here, we'll set graph at v minus 1 and append u minus 1 to that node, or rather that node index, right? So pretty similar structure and logic for these two lines of code to actually build the graph for every single node u and v that are connected by an edge. Effectively, again, each edge would connect these two nodes u and v as our iterators, right? As we actually traverse the input array edges, right? And since the input nodes are always going to be one index for this case, we're actually going to convert them to 0 index. That's where the u minus 1, v minus 1, or even just minus 1 part even comes into play. And we're going to update the graph at those node indices to actually be reflecting the bidirectional edges, right? It's actually going to update, rather I should say, the adjacency list rather than our graph. Okay, so once we actually build the graph, now let's actually define our helper function BFS, right? The breadth first search function. So I'm literally just going to call it BFS. You guys are free to call it whatever you'd like. And for the parameters, it's going to take in one starting value, right? In this case, it's going to perform that BFS from this input parameter, or from this parameter for every single call, the given start node, right? The start is going to be a start node, and we're going to basically use this function to actually calculate the maximum depth of the current connected component from the current starting node start, right? That's our parameter. And to actually set up or initialize the logic of this BFS, first, like I usually do for BFS and even DFS problems, I'm going to initialize my queue. I'm not going to call it queue as usual. It's going to be initialized to a deque, also known as a double-ended queue, starting off with that starting node as we kind of build off from that start node incrementally. I'm also going to initialize something called my distances hash map. Effectively, all we know for sure is that start is going to be corresponding to, of course, 0. Because, of course, the distance of start has to be 0 as we start at the start node, right? And finally, I'm going to initialize my max depth. And this is going to be, of course, initialized to 0. Now, what do these three parameters or variable/data structures really mean? Effectively, this queue is basically going to start and be initialized with the starting node that we're going to build off of for all the nodes as we actually process the current connected component. And the distances hash map is basically going to keep track how far each node actually is from start. Of course, start is 0 units or whatever, 0 away from itself, because it is a self, and the maximum depth is basically going to be the deepest level that we actually reach for this current execution or iteration of our BFS call. Okay, so now let's actually begin the BFS execution, or better known as the BFS traversal. So while the queue is non-null, so meaning while we actually have nodes to process, while it's actually non-empty, we can get the current node. It's basically going to be queue.popleft. Right, and once we actually get the current node, we want to set the current distance to be, we want to set the current distance to be that specific node from the starting node. So basically distances at node, right? Very simple. We're actually retrieving a node from the deque at the leftmost side, popping it off, and getting its current distance from the start, right? And sorry, this should be start, not node. Sorry about that. Rather, I think node will actually be fine as well, right? Basically from the node, right? Because distances at node tells us how far this node index is actually away from the starting node, right? And the starting node is actually our parameter in this case. And now, while the queue is non-null, let's actually explore our neighbors, right? That's very simple. We simply use, our adjacency list graph. That's the entirety of the reason why we actually have that graph for those neighboring neighbors and for the general adjacency list representation or graph representation of the input. So basically, for every single neighbor, I don't know how to spell neighbor. I'm going to assume it's like this, in graph at the specific node, going through all the neighbors of the current node, right? for every single neighbor in this iteration, all the adjacent nodes as such will actually process the unvisited nodes, right? Basically, the way we can actually check that is if the current neighbor as our iterator of the current node, if it's actually not in the distances array yet, we know for a fact that we haven't actually processed it yet. It's still unvisited, and so we can actually process it. So what we're first going to do is actually set distances at that neighbor. This is only if we haven't actually processed it yet, and increment it by 1. Sorry, it should be neighbor, not neighbor. Increment it by 1, right? And not only do I have to increment it by 1, I have to increment it by 1 plus the current distance. So I guess a better way to do that would simply be the current distance plus 1. Right? And now once I actually increment its value, I want to update my maximum depth so far, the maximum depth of the current component, right? And that's going to be equal to the maximum of course, itself, because we don't want to make it smaller by any chance. And of course, distances at the neighbor after we actually increment its distance. Right? Well, if it will be updated if it is. And finally, we want to append to the queue for future processing for future iterations, the current node neighbor. Right, it's a very standard kind of structure for BFS algorithms in general. Effectively, if the neighbor hasn't been visited yet, if it's not actually already in the distances array, we can then assign it as a distance of the current distance plus 1 because it's one more distance away from the starting node from this call, and then update the maximum depth if needed. Right, either update it or maximize it, or just keep it the same if distances at the current neighbor is not greater than the max depth itself, and then add it to the queue for further exploration for its neighbors, right? Basically, you're using it for future executions to kind of explore the entire graph. And now we actually have to check for the non-bipartite graph, right? If in this case, if we don't actually iterate over, or rather check if the neighbor is not in the distances, meaning it has already been processed. We'll have an elif conditional there. We have to check if the graph is actually non-bipartite, right? And the way we can do that is if the absolute value, again, like the problem told us, of distances at the neighbor, this means it's already checked, it's already been processed in this elif conditional minus the current distance. As long as it's not equal to 1, sorry. I'm just making sure I structure this correctly. I think this should be right. Oh, wait. Rather, not equal to 1. Sorry about that. If that's not the case, we have to immediately return -1. Because we've processed this node, we actually find a conflict where two connected nodes are not exactly one level apart. And that means the graph is not bipartite, and so we have to immediately return -1, because of course we are given that the conflict as such, where these two connected nodes, they're not exactly one level apart. They're sharing an edge, but they're not one group apart, like we saw in per se example 2, right? Nodes 1 and 3 were two groups apart instead of one. Their distance, the current distance, and the distances at that neighbor was not equal to 1. In this case, it was equal to 2, which we don't want, and so we had to immediately return -1. We found a conflict and basically checking that the graph was non-bipartite. And effectively, once it's actually done executing, we simply want to return our max depth. But not only the max depth, we want to add 1 to that, because of course, once we actually complete the BFS, we have to return the maximum depth plus 1 as the maximum number of groups. And that is, believe it or not, that is actually the entirety of the BFS algorithm, right? So to kind of reiterate, to kind of fill you in a bit, this is a very lengthy solution. There's a lot of code, and so just be prepared to type out a lot. Okay, well, now let's actually start tracking our visited nodes. The way I'm going to do that is actually initialize a visited set. It's going to be equal initialized to all false times n. So basically, of course, false for all the n nodes, because of course we haven't visited them just yet. And also, I'm going to initialize a total groups, kind of a return variable. It's going to be, of course, initialized to 0. Visited, this array would simply be tracking which nodes have actually been processed or visited yet, and the total groups would simply store the sum of the maximum groups across all of the components. Now, let's actually process each node, right? And the way we can do that very simply using a for loop here in Python is for every single node in the range of n, the number of nodes we actually have, n, we want to basically first check if not visited at the current node. That means, of course, we haven't visited it yet. That means the node hasn't been visited, and so we can actually process its component for every single iteration of each node in the input. So if we haven't visited it just yet, now let's actually find the connected components. So what I'm first going to do is actually initialize my component, and I'll call it component nodes, just to be a little bit more self-explanatory here, I'm going to make it equal to initialize list. And of course, I'm going to get a queue for this iteration to be the double-ended queue. And in this case, it's going to start, sorry, I think it should be like this, at the current node. That's kind of a starting node. And of course, we're going to get visited node to be equal to true. Because that shows that we're now marking it as true because we're now processing or visiting this node in this current iteration. Or simply, the component nodes is going to store all the nodes in the component, and this queue is going to have the same exact purpose, just build off of it for the exploration of its neighbors, to actually find all the nodes in its specific component. And of course here, we're simply marking the current node as true, because now we're actually processing it in this current iteration. We're marking the current starting node as visited. And now, let's actually get our BFS to find all the nodes in the component. So the way I can do that is simply say while queue. So while the queue is not null, while we actually have nodes to actually process, we'll get the current node. I could call it current node. I'm just going to call it current for shorthand. And it's going to be the queue.popleft, popping off the leftmost node of the queue and actually begin to process it, right? Now, once we actually pop off the leftmost queue, I want to then add it to our components. I think I'm going to call it component here. I think that's what I called it here, just making sure. Yes, so component nodes. I'm going to append to my component node, so component nodes out append in Python, the current node. Right, current simply just means current node, guys. And now let's actually loop through all the neighbor nodes of the current node. So for every single neighbor in the graph of the current, again, keep in mind graph is simply an adjacency list. Sorry. The graph at the current node, if not visited, pretty self-explanatory. If we haven't visited the current neighbor, we know we can actually process it and mark it as true, meaning that we actually process it in the current iteration. So first, we'll simply set visited at the current neighbor to be equal to true, because of course now we're actually visiting it. And then we'll actually get the queue at append and append to the queue the current neighbor for future processing of its neighbors, and so on and so forth, right? And here, this is where we actually have to find the maximum number of groups in the component, right? This is just the first part of the solution, if you will. Now we actually have to expand from that. So for every single iteration, we're still in this for loop here, we're still nested. We actually have to, again, find the maximum groups in the current connected component. So once we actually add it to the queue and mark it as visited in our visited array, again, now we're actually going to find the maximum group for the current component, right? So the way I'm going to do this is actually just back down a little bit here. And I think this should be right. I'll double check once I actually finish that up. But first of all, I'll get the max groups and simply call it 0 or initialize it to 0 and loop through every single component node in the current node. So for every single component node in the component nodes, keep in mind component node, not plural, is actually our iterator in this case. In the component nodes array, I'll get my result to basically be a call or an execution of the BFS function. That's the entirety of the reason why we actually used or initialized that BFS function of the current node component node. Alright, so very straightforward here. Once we actually initialize the max groups for the current component, we're actually going to run BFS from each node in the component to actually find its maximum depth for that specific component. And this is where we actually have to check for an invalid graph. So if the result, basically the execution call of this BFS from the starting node as our component node, keep in mind starting node, or rather keep in mind component node as a parameter, simply going to mark that component node as the starting node for the BFS call. If its result is actually equal to -1, that means that we do have an invalid graph for this execution. That means the graph is not bipartite, and so we have to return -1. Right? Again, if any BFS returns -1, the graph is not bipartite, we have to return -1 immediately. Right? That means that this is not a valid graph, as component node is our starting node. Okay? And effectively, once we actually do that, we have to actually update or kind of increment our total groups. And the way we can do that is simply just say the max groups is going to be, of course, the maximum of course, itself, because we don't want to make it smaller by any means. And our second parameter is going to be simply just the result. And again, we're going to actually increment the total groups. So plus equals the max groups, if it was updated or not. And effectively, once this execution actually finishes, we simply have to return the total groups. Why do we return total groups? Because that's going to be the number of groups that we were actually able to form, meeting this problem's constraints Exactly. So if I were to submit this, unless I made any syntax errors here, which I could have possibly made, this would actually be an accepted solution. Okay, yeah. So let me just make sure that my solution works. Give me a minute. Total groups. Okay, so I believe what I did wrong here was, okay, it doesn't look like I misspelled anything as such, which is quite weird. So, so the reason, what the error that I made was actually that my return statement was a little bit too indented. So now this should be an accepted solution. Now this should actually work. Let's just go ahead and double check. Okay, let's see what I did wrong here. Sorry about that, guys. Just a quick syntax error from my end as such. Just kind of double checking my solution here. So we got the graph. So feel free to just fast forward this part if you will. This is just me debugging my very weird code here. Yeah, so this should be n-1, not u-1. Now this should be accepted. Now this should be a valid solution. Let's just go ahead and double check. Or not. Okay, let's go ahead and keep checking. So this is one of the main errors with a lot of code. It's very hard to keep track if everything is right. Just give me a minute, guys. Neighbor in the graph at node. Neighbors on the distances. Alrighty. Okay. Let's go ahead and see what's wrong here. We return the maximum depth plus 1 in the BFS function. That looks completely fine. Let's go ahead and verify this a little bit more here. And I will actually space this out as well. If not visited. Component node. deque visited node is equal to true. That should be completely fine. Okay, so I realized my error. Everyone, sorry about that. This should all actually be indented. Looks like I indented a little bit too much there, or unindented rather. So now this should be an accepted solution. Now this should actually work. Let's go ahead and check if it works real quick. Okay, still not. Let's go ahead and see my error here. Probably another very weird, quick. Okay, yeah. So I don't know why I forgot to unindent this. Now this should be accepted. Probably won't be. Let's just go ahead and keep checking what's wrong. Yeah, so sorry about that, guys. Just me misspelling as usual. So that's quite the weird scenario here. Okay. So I don't actually know what the main issue is as such for this solution. So again, just feel free to fast forward this part. I'm not exactly sure why it's not accepting. Don't know why that is the case. I'll check one last time and then I'll just get into what the code actually does as a whole if it doesn't actually work for some reason. And the really funny part about this is that the code actually did work just around like 20 minutes ago when I first tested out the solution. So I don't actually know why it's not working now, which is kind of an awkward problem in complete honesty. But it is what it is, right? Can't really change it. Return max depth plus 1. And keep in mind, guys, I will actually output or paste in all this code as the final code in my problem description. But let's just go ahead and get into what the problem does as a whole. Effectively, again, what we're really doing here as a whole in this solution, effectively, we're using that BFS algorithm to actually process all the connected components of this graph, right? We're actually processing each connected component of the graph separately, and for each connected component, we're actually using the BFS algorithm to actually determine the maximum depth, which would correspond to the maximum number of groups that we can actually form while satisfying the given problem conditions. And by also ensuring that the graph is bipartite, we can guarantee always that the nodes can actually be divided as required. And of course, if any component isn't bipartite, well then the function, the BFS helper function, would return -1, and that would indicate that it is completely impossible to group the nodes accordingly. So for the runtime complexity here, This is going to be a big O of n plus m solution because, of course, to actually perform the BFS for each node, that would be a big O of n plus m solution. N would be the number of nodes, and m would be the number of edges. And since each node and since each edge is processed a constant number of times, that would be a big O of m plus n operation. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.